Swayam Prabha. Digital India. Educated India.
In this session, the other type of classification techniques, that is unsupervised, would be discussed. In contrast to supervised classification, unsupervised classification requires only a minimal amount of initial input from the analyst. It is a process whereby numerical operations are performed that search for natural groupings of the spectral properties of the pixels as examined in the multispectral feature space. The user allows the computer to select the class means and the covariance matrices to be used in the classification. Once the data are classified, the analyst attempts to assign these natural or spectral classes to the information classes of interest. This is not an easy task. Some of the clusters may be meaningless as they represent mixed classes of Earth's surface materials. This ambiguity is resolved by the analyst who understands the spectral characteristics of the terrain in order to classify clusters into information classes. In unsupervised classification, clustering is one of the most important tasks for data mining and knowledge discovery. It attempts to find subsets within a given data that are similar enough to warrant further analysis. It organizes a set of objects into groups or clusters such that objects in the same group are similar to each other and different from those in the other group. These groups or clusters should have meaning in the context of a particular problem. In clustering, one of the important and fundamental tasks is the definition of a proximity or a similarity function between two data objects, and second, the overall optimization search strategy, that is how to find the best overall grouping according to a optimization criteria. Clustering, commonly known as unsupervised classification, does not need any training data and is specifically useful when the user has limited knowledge about the data. Clustering algorithms partition data into a certain number of clusters, that is groups, subsets or categories. However, there is no universally agreed upon definition. Most researchers describe a cluster by considering the internal homogeneity and the external separation, that is the patterns in the same cluster should be similar to each other, while patterns in the different clusters should not be. Both the similarity and the dissimilarity should be examinable in a clear and meaningful way. The process of clustering can be explained by four basic operations. First, feature selection or extraction. Second, clustering algorithm design or selection. Third, cluster validation. Fourth, result interpretation. This slide shows the flow chart of a typical clustering procedure. We have the data samples which are being represented as data cylinders. This data is then subjected to feature selection or extraction. Based on the results of the feature selection or extraction, the suitable clustering algorithms are designed or selected, which identifies the clusters which have certain spectral groupings in terms of similarities and the clusters are also identified on the basis of certain dissimilarity conditions. Based after the clusters have been identified, then these clusters have to be validated, that is, what is their actual interpretation of the same, what they actually represent needs to be done. Based on this, the result interpretation is carried out, and subsequently this becomes a part of the knowledge which has now been generated from the digital data sets using unsupervised classification. However, we find that there is a reverse flow also, primarily because once the knowledge has been upgraded, this knowledge can now be used again to make certain improvements to the clustering algorithm or to the feature selection procedures which may be there, so that better clusters could be identified subsequently which have meaningful understanding. So, now let us look at each of the 4 basic processes involved in clustering procedure. First is feature selection or extraction. Feature selection relates to the distinguishing features from a set of candidates, while feature extraction utilizes some transformations to generate useful and novel feature from the original ones. Both are crucial to the effectiveness of clustering applications. Proper selection of features can greatly decrease feature selection or extraction. Feature selection relates to distinguishing features from a set of candidates, while feature extraction utilizes some transformations to generate useful and novel features from the original ones. Both are crucial to the effectiveness of clustering applications. Proper selection of features can greatly decrease the workload and simplify the subsequent design process. Generally, ideal features should be of use in distinguishing patterns belonging to different clusters which are immune to noise, easy to extract and interpret. Clustering algorithm design or selection. This step is crucial in clustering as it is related to the selection of a proximity measure and the construction of a criterion function. Patterns are grouped into clusters according to whether they resemble each other. Thus, the proximity measure will directly affect the formation of the resulting clusters. Generally, all clustering algorithms are explicitly or implicitly connected to some definition of a proximity measure. Once a proximity measure is chosen, the construction of a clustering criterion function makes the partition of the clusters an optimization problem. Clustering is ubiquitous and a wealth of clustering algorithms have been developed to solve different problems in specific fields. However, there is no clustering algorithm that can be universally used to solve all problems. Kleinberg states that it is extremely difficult to develop a unified framework for reasoning to diverse approaches to clustering. Therefore, it is important to carefully investigate the characteristics of the problem at hand in order to select or design an appropriate clustering strategy. Next is cluster validation. For any given data set, clustering algorithm can always generate a division, no matter whether a structure exists or not. Moreover, different approaches usually leading to different clusters, and even for the same algorithm with different parameter identification or the order of input patterns may affect the final result. Therefore, effective criteria is important to provide the users with a degree of confidence for the clustering results derived from the used algorithm. These assessments should be effective and have no preferences to any algorithm. Further, It should be able to answer questions like how many clusters are there in the data, or the worthiness of the clusters obtained, or the selection of an algorithm over the others. Generally, there are three categories of testing criteria. These are external indices, internal indices, and relative indices. These are defined on three types of clustering structures known as partitional, hierarchical, and individual clusters. External indices are based on some pre-specified structure which is based on the prior information of the data and used as a standard to validate the clustering solutions. Internal indices is not dependent on external information, that is prior knowledge. On the contrary, it examines the clustering structure directly from the original data. Relative indices places emphasis on the comparison of different clustering structures in order to provide a reference to decide which one reveals the best characteristics of the object. The last operation is the result interpretation. The ultimate goal of clustering is to provide the users with meaningful insights from the original data, so that they can effectively solve the problems encountered. Experts in the relevant fields interpret the data partition. Further analysis, even experiments, may be required to guarantee the reliability of the extracted knowledge. It may be observed that the flow chart also has included a feedback pathway. Cluster analysis is not a one-way process. In many circumstances, it needs a series of iterations. Moreover, there are no universal and effective criteria to guide the selection of features and clustering schemes. Validation criteria provides some insight on the quality of the clustering solutions. However, to choose the appropriate criterion is still a problem requiring more efforts. Now, let us look at the various steps involved in clustering analysis. First of all, we have to acquire the data to be clustered, which requires data acquisition, preparation, and cleaning. The next step is the variables to use, that is, selection of relevant variables for performing the clustering procedure. Irrelevant or masking variables should be excluded as far as possible. The third step is to define a proximity measure. The fourth is to undertake the actual processing of procedure of clustering, wherein the number of clusters have to be identified, and there can be a possibility that even no cluster is a plausible outcome. Thereafter, replication of the same may be required, and finally, testing and interpretation. Clustering methods can be divided into two broad groups: partitioning and hierarchical approaches. Partitioning approach aims to divide the data set into several clusters, which may not overlap with each other, but together cover the whole data space. A data item is assigned to the closest cluster based on a type of proximity or dissimilarity measure. Hierarchical approach decomposes the data set with a sequence of nested partitions from fine to coarse resolution. It can be presented with dendrograms, which consist of layers of nodes, each representing a cluster. This type of clustering is best represented by a dendrogram, which is a tree that splits the data space recursively into small subsets. The simplest approach for hierarchical clustering is to for each individual data points and then recursively merge two closest points, which may be based on a type of distance measure, into a subset until the whole data set is in one cluster. So, based on this, we can now identify the general classification of clustering methods. Under partitioning clustering methods, the next level could be distance based, model based or density based. Density based methods could be further categorized into neighborhood based or grid based, and under each of these we may find that there are different algorithms which have been developed. For example, in distance based we have k-means, Clarence, which are the most commonly used. In model based we have MLE or EM. In neighborhood based we have DBS scan and DOC, and in grid based we have clique and N-class. When we look at the hierarchical clustering, under distance based we have single link or graph based. Under model based clustering schemes we have the Frasley approach. In distance based, under neighborhood we have optics, and under grid based we have grid clustering. Thus, we can see that under different clustering approaches we have different types of algorithms which are available. However, in the subsequent slides I would discuss two very commonly used clustering approaches which are available in commercial softwares. Clustering algorithms used for unsupervised classification of remotely sensed data generally vary according to the efficiency with which the clustering takes place. An example of a conceptually simple but not necessarily efficient clustering algorithm has been used below to demonstrate the fundamental logic of unsupervised classification known as cluster. This algorithm operates in a two-pass mode. In the first part, the algorithm sequentially builds class clusters. In the second part, the minimum distance classifier is applied to the whole data set on a pixel per pixel basis, where each pixel is assigned to one of the mean vectors created in pass 1. So, let us look at the two passes which are there. Pass 1, which is cluster building. During the first part, the analyst may be required to supply 4 types of information. First is radius of the cluster R, a distance parameter for merging cluster C, the number of pixels to be evaluated between each merging of the clusters N, and the maximum number of clusters to be identified by the algorithm C max. To start the process of building of cluster centers, the first pixel of the image is considered to be the cluster center of the first class. Then the second pixel is taken up and its membership for the first cluster is found out by computing the distance between this point and the cluster center of class 1. If the distance between the pixel and the cluster center of class 1 is less than or equal to R, then this pixel belongs to class 1. Now, class 1 has 2 points within its cluster, and the cluster center of class 1 is modified by taking the average value of both the pixels. Now, the third pixel is taken up for examination. If the distance between this pixel and the cluster center of class 1 is less than or equal to R, then the pixel belongs to class 1. Adjust the cluster center of class 1 by taking the average values of all the 3 pixels. If the distance of the third pixel exceeds the distance r, then this pixel does not belong to the class 1, and hence this pixel now becomes the cluster center of a new class, that is class 2. This process of building clusters continues till n pixels have been examined for their membership to cluster of different classes. At this point, the cluster building process stops temporarily and the distance between the class clusters are examined for their separability. The class clusters that have now been identified have to be checked such that the cluster centers of all the classes are separated by a minimum value C. Those clusters which are lying at a distance less than C have to be merged together as they belong to the same cluster. The new cluster center of the merged cluster are now found by taking the weighted average of the old cluster centers being merged. Once the cluster centers have been checked for proper separability, the building up of clusters starts from the point where it had stopped. It is found that the centers of these clusters which have been identified tends to move in its position in the initial phase, and as more points are examined, the positions of the clusters start to stabilize before converging into a fixed position. This process of cluster building continues till the maximum number of cluster centers, that is C max, have been identified or the end of the image is encountered. Finally, the separability of each cluster is checked before proceeding to pass 2. Pass 2 is basically classification of the image. Having identified the cluster centers of all the classes, the classification of the image starts. Each point is assigned a class membership on the basis of minimum distance to mean classifier. When the whole image has been classified, the analyst now examines the classified image. Since the classes that have been identified are basically spectral classes and not information classes, hence the analyst now has to undertake the process of converting the spectral classes into information classes. In this process of convergence, it is found that 2 or more spectral classes may combine together to yield a single information class. This process is rather a tedious, cumbersome and complex, hence requires a great amount of expertise on the part of the analyst in merging many spectral classes into one information class. The next algorithm is the isodata. The full form of isodata is iterative self-organizing data analysis technique A. The isodata algorithm is similar in principle to the k-means procedure in the sense that the cluster centers are iteratively determined sample means. The k-means procedure is based on the minimization of the performance index, which is defined as the sum of the squared distances from all the points in a cluster domain to the cluster center. As input to the algorithm isodata, the analyst has to specify a set of initial cluster centers, that is NC, being represented by Z1, Z2, Z3 and so on to NC. This set, which need not necessarily be equal in number to the desired cluster centers, can be formed by selecting samples from given set of data. For a set of n samples x 1, x 2 and so on to x n, ISO data consists of the following principal steps. Step 1, specify the following process parameters: k, that is the number of cluster centers desired; theta n, a parameter against which the number of samples in a cluster domain is compared. Well, this is generally equal to 3. Theta s, it is the standard deviation parameter. Theta c is a lumping parameter. Capital L is the number of pairs of cluster center which can be lumped together. Generally, this is 2. The next step is to distribute the n samples among the present clusters using the relationship that x is contained within S j if and only if the modulus of x minus z j is less than the modulus of x minus z I for I is equal to 1 to n to n c, where I is not equal to j for all x in the sample data. That is to say that we are now into the process of building the cluster centers based on the information provided at step 1. The next step is to check for those clusters whose membership is below the given threshold value of theta n. That is, we are checking the membership. A minimum membership is required for a cluster to be valid or to be existing. So, in step 3, we discard sample subsets with fewer than theta n members. Step 4, we now update the cluster centers by setting it equal to the means sample means of the corresponding set S j. In the next step, that is step 5, we now compute the overall average distance of the sample from their respective cluster center using the following relationship. Basically, in this particular step, we are looking at the compactness of the cluster, that is its density or the spread of information. A value of d j, which if it is small, it is an indicative of that the cluster is a compact one. In the next step, we compute the overall average distance of the cluster from their respective cluster centers using this relationship d j bar is equal to 1 divided by n j summation of n j multiplied by d j. That is, we are now looking at what is the distance that each cluster is maintaining with respect to each other, or we are looking at its separability between the two clusters which are there. Having done this, the next step is the step wherein we identify whether the clusters which have been identified need to be merged or they need to be split. So, step 3, there are 3 sub rules. If this is the last iteration, set theta s equal to 0 and go to step number 11. If not, then check for the condition that n c should be less than or equal to k by 2. Then go to step number 8. If this is an even number iteration or n c is greater or equal to 2 k, then go to step number 11, otherwise continue. The next step is step 8. Here we first of all find out the standard deviation vector for each of the cluster centers. Having computed this, we now go and find out which is the maximum value of standard deviation which is there, and denote this as sigma j max. The next step, which is step number 10, that is for any sigma max j is equal to 1 to 2 to n c, we find out the condition that whether sigma j max is greater than theta s, and that the condition that d j is greater than d and n j is greater than 2 theta n plus 1, or n c is less than or equal to 2 k, then split the cluster into two centers and increase n c by 1. If splitting takes place, then return to step number 2, otherwise continue. The next step is step number 11. In this, we first of all find out the pairwise distance between all the cluster centers. Then in the next step, compare the distance d j against the parameter theta c. Arrange all the smallest distance which are less than theta c in the ascending order. This is the step where lumping of clusters take place. Having found out the distances between the cluster centers and arranging them in the ascending order, the next step, which is step number 13, is the step where the clusters are merged. The merging of the clusters is done by the relationship as shown here, that is the new cluster center would be defined by the relationship 1 divided by the total number of points in cluster I plus the total number of points in cluster j, and this is to be multiplied by a factor the total number of points in cluster I multiplied by its mean position plus the total number of points in cluster j multiplied by its position of the jth cluster, and we now reduce the total number of clusters by 1. The next step is the step which decides whether the algorithm is to terminate or it is to go back and refine its data. So, if this is the last iteration, then the algorithm terminates. Otherwise, if the analyst wants to change some parameters, go to step 1 or else go to step 2 and continue. In my next session, I will focus on the use of filtering techniques to extract linear feature or boundary lines of features. This process is an extremely important one, specifically if the output from remote sensing data is to be used in GIS based analysis. Thank you.